This work examines gestures performed with a class of input devices with distinctive quality properties in the wearables landscape, which we call index finger augmentation devices, or iFADs. In the large family of gesture sensing devices, iFADs, which are devices that instrument the index finger, hold a privileged position due to the rich interactions they afford on and with the index finger, yet the corresponding gestures have not been systematically examined in the scientific literature. In this work, we focus on iFAD gestures and make the following contributions. We introduce a 4-level taxonomy of iFAD gestures that is index finger centric, encompassing of a large diversity of gesture types, and technology agnostic to be used with a variety of iFADs and gesture recognizers. We conduct a controlled experiment with 40 iFAD gesture types informed by our taxonomy and analyze more than 6,000 gestures collected from 20 participants using a low-cost, custom-made iFAD with a 3-axis accelerometer. We compute and report recognition accuracy rates for iFAD gestures by using popular gesture recognizers readily implementable on wearable platforms. Shilkrot et al. Defined FADs as finger-worn devices with an additional augmentation other than their form that provide a supplemental capability for one or more fingers using the finger itself as a central element. This definition is useful as a starting point for specifying iFAD gestures since it sets the overall conceptual context of devices designed to be worn on fingers. Based on Shilkrot et al.'s generic specification of what a FAD is, we provide an operational definition for iFAD gestures as gestures performed with or on the index finger, detectable by a FAD that is worn on the index finger with the purpose of providing input to an interactive system. This definition is encompassing of a variety of gesture types, and we provide a dedicated taxonomy for which the integrating dimension is the body scale at which gestures are performed with the index finger in the personal, peripersonal, and extrapersonal space of the user. In deriving the categories of our taxonomy, we start from the smallest scale corresponding to gestures performed at the level of the index finger, such as taps on the iFAD, and we progressively consider larger scales and gestures enabled by correspondingly larger body parts, such as the hand and the arm, up to gestures that are fully specified at the scale of the whole body, such as on-body and body reference gestures. We show in the paper how the iFAD taxonomy complements existing gesture classifications from the scientific literature, which are either too generic or too specialized to capture the nuances and diversity of gestures that can be performed with the index finger. To gain insight into the user performance with and perception of iFAD gestures, we conducted a controlled experiment with 20 participants and an iFAD prototype built with a simple accelerometer. We collected more than 6,000 gestures of diverse complexity, from simple taps on the iFAD to specific finger and hand poses, stroke gesture articulations of shapes, letters, and symbols in mid-air, and body reference gestures. We found that iFAD gestures are fast, taking roughly between 1 and 2.5 seconds, and their articulation times correlate positively with their complexity. Also, finger-level gestures require the least amount of mean acceleration to produce, while hand and arm-level gestures the most. We also found that iFAD gestures were generally perceived by our participants as very easy or easy to articulate and socially acceptable in many public contexts involving various locations and audiences. To find out how various gesture recognizers perform on our large iFAD dataset, we used the nearest neighbor approach popularized in the HCI community by the dollar family of gesture recognizers, with several dissimilarity functions for comparing gestures. The highest accuracy rate was delivered by dynamic time warping, followed by the Euclidean, modified Hausdorff, and p$ plus dissimilarity functions. The category of iFAD gestures with the highest recognition rate was represented by arm-level gestures with 98% accuracy. However, the accuracy of the entire set of 40 iFAD gestures was just 83%, which is low according to current standards. To identify a subset of highly recognizable iFAD gestures, we analyzed the confusion matrix of the best recognizer and iteratively eliminated gestures with high error rates. we arrived at the first subset of 34 gestures for which we conducted a recognition experiment and found that accuracy increased to 89%. See condition B in the figure from this slide. We continued our analysis and arrived at 93% accuracy for a subset of 28 iFAD gestures, 95% for 25 iFAD gestures, and 97% for 20 iFAD gestures respectively. See the conditions C, D, and E from this figure. We also reconducted a recognition experiment by randomly selected 20 gesture types from the set of 40, which is condition F in the figure from this slide, and found an average recognition accuracy rate of 89%. These results are very promising given that the gestures were acquired solely from the vantage point of the index finger without sensing any other part of the user's body. We use our results to propose practical implications for researchers and practitioners interested in using iFAD gestures in their own projects. For example, the iFAD gesture taxonomy as a structured space for systematizing interactions based on the index finger enables explorations of many possible gesture types for gesture UI design, from micro-gestures to hand poses to medial swipes to on-body input. Designers should capitalize on the diversity of iFAD gestures towards gesture-based UIs featuring interactions that are expected to be fast, low effort, and highly acceptable for users. Also, by adopting the vantage point of the index finger, a diversity of gestures can be reframed, such as an on-body gesture described as an iFAD gesture. This reframing can influence the choice of technology to sense gestures, for example, an electronic ring with motion sensing instead of a touch sensor integrated in the pocket. Please see our paper for more details. Thank you.